Okay, so today we're going to talk about the Cartesian plane, distance, and midpoint. So here is the Cartesian plane, named for philosopher and mathematician René Descartes. So here's our classic x-axis and y-axis. And so one, I'll just say, yeah, this is the Cartesian plane, again, named for René Descartes. Sometimes it's referred to as R2. So not squared, we say R2. And the way this is defined, so you remember that R was the set of real numbers. Well, this is how we denote the real plane. So R2 is exactly the set of all ordered pairs xy such that x and y are real numbers. So yeah, when I refer to R2, I am talking about the real plane, and in terms of a set, we think about it like this. Now, sometimes instead of Cartesian coordinates, you'll hear this referred to as rectangular coordinates or a rectangular system. So why might it be called rectangular coordinates? Well, let's consider a point that's in the plane. Let's take, for example, maybe 3, 2. So let's plot 3, 2. So 3, 2. Remember, that means we go over 3 and up 2. Well, think about this, right? So this is exactly 3 units over and 2 units up. And you can see with the coordinate axes, this makes a rectangle. Okay, so yeah, let's just note. So when I talk about an ordered pair xy, well, if x is positive, I'm going to the right. And if x is negative, I'm going to the left. Well, if y is positive, I'm going up. And if y is negative, I'm going down. The origin is quite a special point. That's 0, 0. And of course, there's 4 quadrants. Starting here, this is quadrant 1, quadrant 2, quadrant 3, and quadrant 4. So I'll denote that with Q1 for quadrant 1, Q2 for quadrant 2, Q3 for quadrant 3, and of course Q4 for quadrant 4. And so let's make some observations about the points that are in each quadrant and in terms of x's and y's being positive or negative. Okay, so observations. Well, in quadrant 1, let's take a look, right? So if I'm in quadrant 1, it looks like the x's are positive and the y's are positive as well. Let's note that. So x is positive. Now greater than 0 means positive, so I'll often say positive for this. So x is positive and y is positive in quadrant 1. And you can clearly see that. Now what about quadrant 2? Well, if I go to quadrant 2, you can see if I pick any point inside of quadrant 2, the x value is going to be negative and the y value is positive. So yeah, x is negative, less than 0 means negative. And the y is positive in quadrant 2. Okay, that seems fine. Now, what about quadrant 3? Well, notice that both x and y are negative in quadrant 3, right? So if I pick any value that's in quadrant 3, the x is certainly negative, the y is also negative. So x is negative and y is negative in quadrant 3. And then lastly, quadrant 4, right? So in quadrant 4, it looks like the x value is positive and the y value is negative. So let's note that. So the x value is positive in quadrant 4 and the y value is negative. Now, sometimes when we're talking about the x-axis, we'll refer to it in a different way. Notice there's a special feature that the x-axis has. If I pick any point that's on the x-axis, what can you tell me about its y value? So it doesn't matter if I pick this point or this point or this point or this point, the y value is 0. So maybe we should note that that's pretty special. So we're going to say the x-axis is also called y equals 0. So the x-axis is also called y equals 0. And that makes complete sense because, again, for any point that's on the x-axis, the y value is always 0. Well, if that made sense, then maybe the next is not a big surprise. What about the y-axis? What's sort of a defining feature of any point that lives on the y-axis? Well, if I pick any point that's on the y-axis, the x value is clearly 0. So it makes sense to call the y-axis x equals 0. And I encourage you not to think about it as this sort of opposite thing, but really think about just what it means, right? So instead of saying like, oh, the x-axis goes with this opposite y equals 0, you don't want to think like that. You want to say, okay, if I choose any point on the x-axis, what's the defining feature? The y value is 0. And analogously, if I pick any point that's on the y-axis, the x value is 0. We always want to go for logic over sort of tricks. So yeah, the y-axis is also called x equals 0. Okay, so let's talk about some symmetry properties. Okay, so definition. So we're going to say 2 points let's say x1, y1, and x2, y2 in the plane are said to be one, symmetric about the x-axis. Let's see if we can come up with a rule for this. Let's see if we can sort of reason this out. So we'll say symmetric about the x-axis. Okay, so let's take a look. So drawing the Cartesian plane. And let's pick some point. Let's call this x1, y1. And then symmetrically, so we're going to reflect about the x-axis. So symmetrically, we have this. Okay, and do assume that the distance from here to here is the same as the distance from here to here. So assume that these distances are the same. Well, what could we say? Well, we could say, well, notice that the x's are in the same spot. So we would say, well, if x1 equals x2, if both x's are in the same place, and they are, right, they're at this value right here, which means those have to be equal if they're in the same place. And then the y's have to be negatives of each other. And so y1 is equal to negative y2. Again, the key thing here is we're assuming these distances are the same. Maybe I'll cheat a little bit, make the point a bit bigger. Okay, so we could say something similar about symmetry about the y-axis. So yeah, 2 points x1, y1, and x2, y2 in the plane are said to be symmetric about the y-axis. And again, let's take a look at a picture and we'll see if we can sort of reason this out. So let's say here's x1, y1, and I want this distance to be the same as this distance, so assume that it is. That's x2, y2. Well, what happens if these 2 points are symmetric about the y-axis? Well, notice that the x values are, they're not equal, right? But they're sort of negatives of each other, right? So this x value is the negative of this x value, right? Again, assuming these distances are the same. So we've got x1 is equal to negative x2. And notice that the y, they're in the same spot. They must be equal, right? They're in the same spot on y. So y1 must be equal to y2. So that's a second type of symmetry we care about. Let's talk about symmetry about the origin. So 3, yeah, our 2 points in the plane are said to be symmetric about the origin if, again, we'll try and figure it out. So what does that mean to be symmetric about the origin? Well, if I pick some point, say this is x1, y1, then the distance from here to the origin needs to be the same as the distance from here to here. Again, so assume these distances, this distance is the same as this. And let's think about what happened. So notice that this x value is the negative of this x value. So we need x1 to be equal to the negative of x2, and you can see that, right? This x value is the negative of this x value. But what about the y's? What can I say about this y value versus this y value? Well, they're also negatives of each other. So I would say that y1 is equal to the negative of y2. Okay, so with that said, let's go ahead and try an example. So for example, let's go ahead and let A be the point 1 minus 3. And so with this, let's go ahead and find the points that are symmetric to this point about the x-axis, about the y-axis, and then about the origin. Okay, so find the points that are symmetric to A about the x-axis, the y-axis, and C, the origin. Okay, so yeah, let's go ahead and try that out. Okay, so first, let's talk about the point that's symmetric to this about the x-axis. So I'll say this is my x-axis and this is my y-axis. And so we said A is the point 1 minus 3. So let's plot that. So let's assume, let's give this sort of a scaling. So we'll say that's 1, 2, 3. We'll say that's 1, 2, 3. So we've got the point, so 1 minus 3. So that's over 1 down 3. So that's the point A. And so we want the point that's symmetric to A about the x-axis? Well, think about this. I want this distance to be the same as this distance, so that means I would land here. And I'm going to call it A sub x. And so what's our new point? Well, the point that's symmetric to A about the x-axis is this point. Well, this is exactly 1, 3, but we notice that goes with our rule, right? The x value stayed the same, and it makes sense, right? We're in the same x location, so the x value should stay the same, and then the y's are opposite of each other. So that makes complete sense. Okay, so now we want to take A, and we want to find the point that's symmetric about the y-axis. So that means we want this distance to equal this distance. So this would be, let's call it A sub y. And so this point right here would be -1, -3. But that's completely in line with our rule. Let's think about it. If I want to find the point that's symmetric about the y-axis, notice that the x values are opposites of each other. So it makes sense that the x values negate. But I'm in the same location on y, so it makes complete sense that the y values here are the same. So you notice the rules make sense. I sort of do a spot check with some geometry, and the rules make complete sense. Okay, and so now what we want to do is we want to look at a reflection of A through the origin. So what does that mean? Well, that means I want this distance to be the same as this distance. So that means I should land here, right? So if you think about this, I'm going to land here as I reflect through the origin. So I'll call that A sub O. So that this is a reflection of this point through the origin. So this distance is the same as this distance. And so where did I land here? I landed at -1, +3. And that makes sense, right? So you notice that the x values are opposite of each other. Makes sense because I went from here to here, and the x value here is -1. And the y values are opposite of each other. That makes sense here because there's 3 and there's -3. So let's make some observations regarding reflections. So yeah, if I want to talk about a reflection through the x-axis, what happens? Well, I'm just taking the opposite y. If I want to take a reflection through the y-axis, I'm just taking the opposite x. And if I want to do a reflection through the origin, both of these become their opposites. So let's call this observations regarding reflections. So we'll say to reflect, the point xy about 1, the x-axis. Well, the observation that we made was replace y with its negative. Well, 2, if I want to reflect xy about the y-axis, then I should replace x with its negative. And there's sort of this understanding that we sort of keep x the same. And here we keep y the same. And then lastly, if I want to reflect this about the origin, I need to take the opposite of both of these. So 3, to reflect this about the origin. So we replace x with negative x, and we replace y with negative y, or minus y. Okay, so the next thing we want to talk about is this idea of distance. And in order to talk about this in the amount of depth that we want to, we first need to go back to geometry just for a little bit. We actually want to state and prove the Pythagorean theorem. So I'm going to say, well, before we discuss distance, we need the Pythagorean theorem. So let's recall the statement. I'm going to star this because there's a version that's a little bit more complete, and I'll mention that, but we only need this one particular version of the Pythagorean theorem. So we have the following. So if triangle ABC is a right triangle, then a squared plus b squared equals c squared, where a and b are legs and c is the hypotenuse. So this is the version that we need. The more complete statement would say triangle ABC is a right triangle if and only if a squared plus b squared equals c squared. That would imply that the implication goes both ways. And what that means is if this triangle is right, then the equation holds. But going the other way, which we don't need right now, but going the other way is if the equation holds, then the triangle is a right triangle. So that's why I put the star there, because again, this is what we call in math a biconditional. If I wrote it the full way, the full version right here, but we only need this sort of half of it in a sense, this conditional, this implication. Okay, so let's prove the Pythagorean theorem. So again, I know this seems out of nowhere, but since we're going to discuss distance, this actually comes into effect. So it's nice to have a nice foundation for the Pythagorean theorem. So here's the idea of the proof. So let's consider the following. So let's say we have a square within a square, and we have exactly this setup. Right, so what I want to do is sort of make an observation. What would be the area of the entire square? So the area of this. Well, it should be this side times this side, right? So base times height. But what is the length of the base here? Well, this base right here has length a plus b, because you have a and you're adding onto it b more units. So this has length a plus b, and then so does this. And if I want the area, I just need to take the product of the two dimensions. Again, that would give me the area of the whole figure. What I then want to do is I want to compare that to the area of these 5 little subfigures. Notice I have 4 right triangles and then this sort of smaller square inside. So let's sort of deconstruct this. Okay, so we've got this, right? What else do we have here? We've got 4 of these. So 1, 2, 3, 4, and I'm not putting them down in any particular order right now. There's a few neat geometric things we could do, but I just want to note that we want the area of these 5 figures. And that should be the same, right? That should be the same as the area of this entire square. So yeah, let's say that. Okay, so there's 4 of these, right? So there's 4 of these right triangles, and there's 1 of these. So let's see, what would the area of all of that be? So let's see what we have here. So this would be, let's see here. So the area would be base times height. So if it bothers you like this, we can certainly rotate. That won't change the area. So base times height. So the area is going to be c times c, which is c squared. And then I've got 4 of these, right? So I have 4 of these, and it's a triangle. So the area should be 1/2 base times height. Okay. And so maybe we'll put that in an equation here. Let's see what we have here. So for the area of the entire square, we said that was base times height, right? So we've got a plus b times a plus b equals, and we said the area of this plus, we then mentioned we had 4 of these right triangles. And that makes sense, right? The total area equals the sum of all the little area pieces. Okay, so let's do some algebra. So here we have a squared plus ab. So I'm just using the distributive property as I multiply. That's ab. And this, lastly, of course, is b squared. Here we've got c squared. Well, 1/2 of 4 is 2. And we have some like terms here that we can combine, right? So let's combine our like terms. And hey, look, we can subtract this from both sides. Let's do that. So I'm going to subtract it from the right side, and I'm also going to subtract it from the left side. And we get our result. Hey, that's pretty cool. So that means the Pythagorean theorem is true beyond the shadow of a doubt. Okay, so now we can move into distance. We will use the Pythagorean theorem in just a little bit, but first let's talk about distance in the number line. Okay, so here's our number line, our complete number line. That's a visual representation of the set of all real numbers. And let's say I want to talk about the distance from A to B. Well, the distance from A to B is denoted by this sort of absolute value. So that denotes distance. So the distance from A to B is the absolute value of B minus A. But let's notice something. The distance from A to B is this, but we could also say it the other way. So the distance from A to B is also the distance from A to B. So this length, it doesn't matter if I travel from left to right or right to left. I'm talking about the same distance. That's the same length. So let's view that maybe in more of a concrete sense. So let's say we have the following. Let's say here's 0, here's 1, here's 2, here's 3, 4, etc. And let's say I want to talk about the distance from 1 to 3. So the distance from 1 to 3, so this length, this distance from 1 to 3, we denote like this. So distance from 1 to 3. And we can see that's exactly 2 units. But let's make another observation. This is the same distance if I take the distance from 3 to 1. That's also 2 units. So 1, 2. So whether I went here, 1, 2, or I go here, 1, 2, I'm talking about the same distance. And let's look at maybe another example. Let's say here's -2, -1, 0, 1, 2. Let's extend that out. Let's go to 3 maybe. Why not? So let's say we want the distance from -2 to 1. There's a couple ways we can think about that. Well, the distance from -2 to 1, that distance right here, I could express it like this. So the distance from -2 to 1, well, that's exactly 1, 2, 3 units. But I could also walk the other way, right? So I could say, okay, well, the distance from -2 to 1 can also be thought of in this way. So 1 minus -2, the distance from 1 to -2. Well, that distance is exactly 1, 2, 3 units. So let's make an observation about these quantities and where we land. So these quantities and where we land in terms of distance. This brings us to a sort of a formal definition of absolute value. And so the absolute value of x is equal to, well, let's think about it. If the quantity inside is positive, like it is here, then I get exactly x. So this quantity is actually 2. This would be a positive 2. And notice I get that same positive 2. So if this is positive, I get this 2. So the absolute value of stuff, when stuff is positive, is just stuff, right? So if that's positive quantity, I get the same thing back here. So the absolute value of x is equal to x precisely when x is non-negative. Okay, so it returns the same thing. But it's a little bit different here. So if we want to have this distance idea make sense, let's take a look here. Well, notice that this is actually -2. How does this compare to this -2? Well, if this is negative, to get that, I take the negative of it. So yeah, if this is negative, then I end up taking the negative of that to get this. And that would make sense because I'm talking about a distance. I want a non-negative quantity for my distance. So yeah, if this input is negative, then to get the distance out of this, I take the negative of that negative to get that. So that's going to give me negative x. Okay, so this will output negative x if the input is negative. And again, just for to be crystal clear, so this is really -2. And to get 2, that's exactly the negative of -2. And so that's 2. So that's what this means. If the input is negative, then to get the absolute value or the distance, I take the negative of that negative. If the input is positive, then I return exactly the same input. And in this way, I get a meaningful distance. Okay, we can also think about it like this. Let's say here's 0 and here's x. So in this case, x is positive. And so you can see, well, if x is positive, then this distance is going to be the same value x. Okay, it's to the right of 0. And so this absolute value or distance to 0 is exactly this. Well, if x is to the left of 0, and I want this distance, if this is to the left of 0, it's clearly negative. And if I want to return a distance, then I should take the negative of this because this length is x, and this x is negative. And if I want to return a non-negative distance, I need to negate that. So yeah, if the input is negative, if that's negative, then this outputs the negative of that negative so that you get a meaningful distance. If this input is positive or non-negative, then it outputs the same value. And again, in that way, you get a meaningful distance. Okay, so we can compute distance on a number line. Now, what about distance in the plane? Okay, so let's suppose we have 2 points that are in the plane. Let's say here's A, and let's say here's B. And we really want to know the distance from point A to point B, which is essentially this length, isn't it? Yeah. So if I want that distance, we have to be kind of clever about this. So let's label our points. That's my first point. Let's go ahead and label that point x1, comma y1. So yeah, that's the point x1, comma y1. And let's go ahead and label this point x2, comma y2. Now here's where we get kind of clever, and here's where the tie-in with the Pythagorean theorem comes to play. Well, any line segment I can actually think about as the hypotenuse of some right triangle. So let's take this line segment, and let's think about it as the hypotenuse of a right triangle. So pretty clever, right? Neat idea. Well, let's label this point. Oh, keep in mind, I'm picking this specifically so this is parallel to the x-axis and this is parallel to the y-axis. Okay, so this point right here, so that has the same x location as that point, right? If you were to drop down here on the x-axis, they're both in location x2. That is in location x1. So the x-coordinate should clearly be x2, right? Should match that one because, again, if you dropped a vertical line, they both live on that same vertical line. And then what about the y value here? Well, the y value here should be the same as this y value. So let's call that y1. Okay, so let's see here. How should I refer to this leg of our right triangle and this leg of our right triangle? Well, isn't this length, if you think about what we just talked about, just the distance or the absolute value? So this is just the distance from x1 to x2. So right here. So I should call this length, so the length from here to here, I should call that the absolute value of x1 to x2 or x2 to x1. Actually, it doesn't matter which order I name them in because it's talking about distance. You'd be referring to the same distance. So whether I write x2 to x1 or x1 to x2, this is computing the distance. Well, similarly here, I want to compute the distance. And so this will be the distance from y2 to y1. And again, because I am talking about distance, I could write it in the other order. Okay, so let's say we want this length, the distance from A to B. Let's call that D for distance. And so by the Pythagorean theorem, we know that leg squared plus leg squared is equal to the hypotenuse squared. But using the definition of absolute value, you should convince yourself that it's perfectly fine to write x2 minus x1 quantity squared plus y2 minus y1 quantity squared equals the distance squared. And that's because, well, say the inside was negative, squaring it would get rid of that -1, and so I'd be fine. And if the inside was positive, squaring it would keep it positive. So it's actually just fine by definition of absolute value to go from here to there. If that's confusing, I encourage you to really think about it. Go back to the definition of absolute value. See if you understand it. And by algebra, we can solve for d. So by taking the square root of both sides, I get the square root of x2 minus x1 quantity squared plus y2 minus y1 quantity squared. And that's our distance formula. So that's in some sense like our math measuring tape in the plane. That's going to give you the distance from one point to another point in the plane. And that's the distance specifically if I connect by a line segment. There are other ways in calculus to compute a distance if I were to, connect by a curve, but that's a whole different matter for calculus. So let's state formally this distance formula. Just kind of summarize what we talked about here. So I'll say the distance formula so I'm going to say the distance d from point A, which is x1, y1, to point B, which we're calling x2, y2, is exactly what we just found. So d, the distance, is equal to the square root of x2 minus x1 quantity squared plus y2 minus y1 quantity squared. And with that said, let's go ahead and try an example, right? So example, so let's see, what is the distance from -1, 2 to 3, 4? Well, we know we can compute that using our distance formula. So let's write out the distance formula and carefully think about what's x1, x2, y1, and y2 in this case. Okay, well, we can clearly label these. This would be x1, it's my first x. This would be y1, it's my first y. That makes this x2 because it's my second x, and this is y2 since it's my second y. Now, with that said, if I understand that, I can just go ahead and drop these in the formula. So I need x2 minus from the formula, parenthesis, x1 quantity squared, plus, let's see here, so y2 minus y1 quantity squared. Okay, not bad. So this looks like 4 squared plus 2 squared. And so what does that give us? That looks like the square root of 20. And we could simplify that. What's the biggest perfect square that goes into 20? Well, it's 4. So I can think about this as 4 times 5. Now the square root is multiplicative. That means I can split it up over products. And that is exactly 2 radical 5. And that's the exact distance from this point to this point. Notice in mathematics, we have the luxury of exactness. We don't need a decimal here. Decimals are great in applications. They really are. But for us, for this particular problem, we can give the exact distance. So that's pretty nice. Okay, let's try one that requires a little bit of thought and care. So quite a cool problem here. I like this one. So let's see what we have here. So for example, find all points with x coordinate 1 which are 4 units from the point 3, 2. So before we go solving this, let's try and reason through what we might be looking for. So find all points with x coordinate 1, which are 4 units from the point 3, 2. Okay, let's say here's 1, 2, 3, 4. So that's x and y. Now, all the points that have x coordinate 1, they live on a line, right? So all the points that have x coordinate 1 should live on exactly this line right here. It's known as the line x equals 1. So let's consider the point 3, 2. So 3, 2. And we want all the points that have distance 4 or are 4 units from this point. Okay, we definitely don't want to guess, right? So maybe there's some mystery point here. We'll end up letting the algebra do the talking, but that at least gives us sort of a clue on how to perhaps solve this. And maybe I could go 4 units this way and find another point. But that's what we want. We want all the points that have a distance of 4 units from this point, but they have to have an x coordinate of 1. So that's sort of our extra stipulation. So let's try this out. So all these points that are on this line, let's think about any point that's on this line as 1, because the x value is fixed, comma y. Right? Because if I live on this line, the x value is always 1, but the y could be anything. And then I want the distance from here to this point, right? So this point we said was 3, 2. And we want that distance to be precisely 4. Interesting. So let's make sense of this. Since we're talking distance, we'll start with the distance formula. And so it makes sense this might be x1, this is y1, this is x2, and this is y2. Okay, so x2 is 3 minus x1, which is 1, plus, now y2 is 2, right? That's my second y value, minus y1, my first y value, so that's y. And what do we want this distance to be? We want this distance to be exactly 4 units. So we want the distance to be 4. It looks like our unknown in this case is the y value. Okay, so let's take a look. Let's maybe combine this right here. So 4 is equal to, that's going to be 2 squared, which is 4. And I'm not going to multiply this out. Let's see if something nice happens algebraically if we don't. Now, to get rid of the square root, I'm going to square both sides. So this is positive. I don't have much to worry about here. So 16 is equal to 4 plus 2 minus y quantity squared. I'm going to subtract 4 from both sides. That's going to give me a 12. Let's go ahead and take the square root of both sides. That's going to give me plus or minus the square root of 12. That's equal to 2 minus y. And then I can subtract 2 from both sides. But then I just have to remember to multiply everything by -1 because I'm trying to solve for y. So that's going to give me 2 minus or plus when I multiply both sides. Those will switch. Radical 2 equals y. And it looks like there's 2 points that have a distance of 4 units from this point that live on this line. Okay, so we know that the x value is fixed at +1. And so one of our y values, so given by this, is 2 minus the square root of 12. But we have a second point. Again, the x value is fixed, it's 1. And the other y value is 2 plus the square root of 12. How might I check? How could I check? I'm going to leave the check to you as an exercise, but you could look at the distance from this point right here to this point using the distance formula carefully, and you should get 4. Well, same thing here, right? If I wanted to check, I should look at the distance from this point to this point, and it better be 4 units. Okay, so next, let's talk about the midpoint formula. So here's the idea. Let's assume I've got a line segment with endpoints A and B. So here's an endpoint. So A, let's call that maybe x1, comma y1. And let's say here's B. And let's call that x2, comma y2. And we want the point that's right in the middle, M, the midpoint. There we go. So the midpoint M of the line segment with endpoints A and B is exactly, well, the midpoint is, now we're going to take the average of the x's, right? That's going to bring us to the middle x value. So take the average, so add them up and divide by 2. The average of the x's, comma, the average of the y's. But how do I know that's actually the midpoint? I'm just claiming that it's the midpoint. Maybe it's some other point. Maybe I did this incorrectly. So now we want to really convince ourselves that this truly is the midpoint, the middle of the line segment. Well, if this is the midpoint, it should cut this line segment in half. That means that the distance from here to here, so from A to M, should equal the distance from M to B. So that's how we're going to convince ourselves that this truly gives the midpoint. We're going to compute these distances and see if they're equal. Well, if they're not equal, then this point didn't cut the line segment in half. So yeah, we're going to go ahead and check that. We want to really convince ourselves. We want to let the math do the talking. So we're going to say, well, if M is indeed the midpoint, of line segment AB, then the distance from A to M should be exactly the distance from M to B. So yeah, we just have a couple of distances to compute. And so let's go ahead And we're going to find the distance from A to M. It might be a good idea to just remind ourselves that we said A was exactly x1, y1. The midpoint was exactly x1 plus x2 over 2, y1 plus y2 over 2. And we said B was the point x2 comma y2. So that'd be good to reference. Okay, so first we want the distance from A, so from point A to point M. And of course, we're going to use the distance formula. So let's just maybe remind ourselves, what is that distance formula? So D is equal to the square root of x2 minus x1 quantity squared plus y2 minus y1 quantity squared. Okay, so we're looking at these 2 points right here. So we want x2. So what's playing the role of x2? This object here. It's just our second x value. So that's x1 plus x2 over 2. Minus what's playing the role of x1 here? Well, it's exactly x1. So we're going to take that quantity squared. And then here, so we want to bring this, think about it in context here, right? So what's playing the role of y2? It's exactly this, just because it's our second y value. So that's y1 plus y2 over 2 minus y1. That's going to be quantity squared. Okay, so let's go ahead and do just a little bit of algebra. Now let's get common denominators, right? This has a denominator of 2, but this doesn't. So we can just multiply the top and the bottom by 2, and same thing here. And that way I can write this as a single fraction, same thing here. Okay, so what combines? So let's see here. So I'll have an x2, and x1 minus 2x1 should be minus x1. That's over 2, quantity squared. And here, so I have y2, and then y1 minus 2y1 is exactly minus y1. That's over 2, quantity squared. I'm actually going to leave it because I don't need to take this much further. I just want to see if I can get this distance to match that. And if I can, then they're equal. Okay, so now let's find the distance from M to B. Well, again, using the distance formula, so using the distance formula, but in the context of these 2 points, let's see what we have here. So we have x2, right, minus, now be careful because there's multiple terms here. So we want this minus this. It's like the second point's x value minus the first point's x value. Right? And we're just going to do that carefully. Quantity squared. Plus, now I need to take care of this in context. So the second point's y value minus the first point's y value. So no matter how exotic these look, right, it's just, it follows this carefully. So that's y1 plus y2 over 2, quantity squared. And we're just going to do some algebra now. So using the same thinking as before, we can call this 2x2 over 2 just for common denominators. We can call this 2y2 over 2. And let's go ahead and distribute the negative here. I'm going to show maybe one extra step. So I do have my common denominator of 2. That's nice. And so I distribute the negative, so don't forget to distribute that to both terms. So that'll be minus x1 minus x2. And same thing here. I do have my common denominator. And so that's going to be 2y2. And then go ahead and distribute carefully that negative. So that's minus y1 minus y2, quantity squared. And so let's see, can we combine these? We sure can. So that's x2 minus x1, because those are like terms, aren't they? They combine. That's going to be quantity squared. And then these will combine. So this is very promising. That's over 2. Hey, look at that, though. That's exactly that quantity here. So I could actually call that, since this quantity is equal to this, I get that this is the distance from A to M. Therefore, M is the midpoint of line segment AB. Very cool. Very, very cool. And that's the nice thing about math, right? So you might have an object where, we claim it's the midpoint, but and now you know for certain the math said it has to be. It has to be. Because it bisects the line segment, or it cuts it in half. All right, let's do an example. So yeah, let's go ahead and find the midpoint of the line segment connecting the point 1 minus 5 to the point 7, 4. And so we know for certain that the midpoint is just the average of the x values, comma, the average of the y values. Okay, so let's go ahead and set up the average of the x values and set up the average of the y values. So this gives me, it looks like 8 halves, and this gives me, so that's going to be minus 1 half. But of course we can reduce that. And so this gives us 4, minus 1 half. And you should think to yourself, how could I check this to be certain? We can compute some distances, right? Because the distance from A to the midpoint should equal the distance from the midpoint to B. So just to set up the next lecture, this is going to be important because it's going to help us talk about circles in the plane. So next lecture, we want to talk about circles and completing the square, which will help us find the center and radius of a circle.